I'm not entirely sure that our next speaker needs an introduction per se. I'm sure that many of you have come here, at least in some large part, to get to meet Pierre. I actually found out about Pierre when I was in grad school, and I sent him an email, and I was really surprised he wrote me back almost immediately. And I didn't think anything of it for a couple of years. I actually had a question about planetary formation. And it was interesting. And then, some years later, we started up this podcast, and we actually reached out to Pierre. And, I don't know if you guys are aware of this, but when we started this podcast, we actually used puppets, right? Because we were very afraid of being people on the internet, right? We figured if this podcast succeeded, we would have millions of viewers, and we didn't want people to be stopping us on the street. Billions of viewers, yeah. So we tried these little puppets at first, and it was a disaster. Actually, Pierre was the one who talked us out of being puppets, just so you know. But needless to say, he agreed to do the show. We did 4 different podcasts with him, and you can listen to them audio only if you don't want to be distracted by the alien puppets. We went all the way through his illustrious career, starting with MRI and moving into all of his astrophysical work. But over the years, it's just been a real pleasure, a real joy of my life to have gotten to know Pierre. I have the pleasure and privilege of speaking with him regularly on the phone, and he's kind of become our science dad a little bit. When you leave grad school, you don't have an advisor anymore. You don't really have anybody to tell you when you're going off the rails. And I just really appreciate that you've been in my life to be that person. And so I couldn't think of a better keynote speaker for us on our first DemystifySci conference. And I hope this is the first of many, than to have Pierre here to speak with us about his revolutionary ideas. And I do think that if you don't know Pierre's work, which you probably do, but if you don't, this is probably one of the most important living scientists that we have in this tiny little room with us today. As far as somebody who's going to absolutely revolutionize the way we think about the physical universe that we live in, I think that his ideas are very simple and elegant and easy to understand. You can probably go home and explain them to your little cousins. There's nothing, of course, the details can get a bit hairy, but the overarching idea that the sun and the stars in general require a material basis to be comprehended, I think is absolutely essential to our progress moving forward in terms of not only just understanding who we are in this universe, but in terms of getting towards a cleaner way of existing on this planet, a more harmonious existence with respect to our, for lack of a better word, the environment, the world that we live in. And I think that understanding how the stars work is a great step towards that. So welcome, Pierre. Thank you so much for being here. It's a real honor.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
All right. Now, well, she didn't want me to do this, but I would just... Now, I've been married for 44 years. And, I can't tell you how much I love my wife, but I'll try not to cry. But I'll tell you a story of Patty. People say that behind every man, there's a great woman, but for me, she's just been a leader. And I'm so crazy about it. But, okay, sorry. I'll tell you a story about Patty and about life philosophy. And Patty, when she was a little girl, she used to play croquet. And she never croqueted somebody. When you hit the ball, you get to put your foot on your ball, and then you get to croquet the other person far away, and then you lose your turn. But Patty always thought that she should go through the next wicket. So in life, you shouldn't croquet because if you do, you'll hit your foot. So Patty has been a great example of how to do things. She reads all my scripts on Sky Scholar, and she does make sure that I try to keep a kind heart towards others. I try to say one thing about science, which I told people today that you always have to be generous towards others, even when they disagree with you. You have to remember to love them. And I look at science in a way, it's a lot like a chess game, you know? If you're a good chess player, be kind to your opponent. Don't ridicule him. And so for me, the chess game is kind of already over. People maybe have not caught up with me. I had a friend, John Wilkins. He was a great physicist at OSU. And he had come there from Cornell, had trained at Cambridge, and had worked with Schrieffer, the Nobel Prize winner. And John would always tell me, he says, Pierre, don't be discouraged. You're just 30 years ahead, and they'll catch up to you eventually. I played this video, which we won't play again, but it had some beautiful pictures of the sun.
There it goes.
And, you know, the sun is... I never cared about astronomy when I was a student, by the way. I never took an astronomy class, and I kind of fell into astronomy. Kind of by accident, kind of against my will, and it's a difficult path through MRI to get to astronomy, but in any case, God brought me that way, and that's why I'm here today. So we'll start with the photosphere, and the photosphere, of course, is that portion of the sun that we see, the visible portion of the sun that we see in the visible light. And the photosphere is characterized by a spectrum that looks very much like a black body. And for me, this is the only proof that's required to establish that the sun is actually condensed matter. Once you understand the basis of thermal radiation, you realize that, first of all, that Kirchhoff, when he wrote his law in 1859, Kirchhoff wrote his proof. So Kirchhoff's law says that within every enclosure that's opaque, within that enclosure, the radiation will also always be black and determined only by temperature and frequency. And he did this mathematically, and after he did the proof in 1859, those mathematical proofs fell away. And Hilbert in 1913 actually wrote that there is no mathematical proof of Kirchhoff's law anymore, and there isn't. And there also is no experimental proof of Kirchhoff's law. Now, the problem for astronomy is that in the gaseous sun, you absolutely need Kirchhoff's law in order to account for this spectrum. We do use Wilt and Chandrasekhar advanced the negative hydrogen ion as part of explaining the thermal spectrum of the sun. But the problem is that for other star types, when they get hotter, negative hydrogen ion doesn't work anymore. So it just deconvolves. So what I say is, look, to get a thermal spectrum, you need a lattice, and this is what's missing in physics. I say that the great black hole in physics today is a lack of understanding that you need a thermal lattice in order to produce a black body spectrum. Now, speaking of Chandrasekhar, I really enjoyed his talk this morning, and I just wanted to mention that Chandrasekhar had also worked with Born in Copenhagen, and of course, Chandrasekhar, who was the father of the white dwarf and the Chandrasekhar limit, well, you could assign maybe Eddington was the one that first proposed that stars would be hyperdense and become white dwarfs. But Chandrasekhar is the one who really brought our modern understanding of the gaseous nature of the stars, and he had worked with Born and with Bohr, and then he also was the nephew of Raman. So how did this very strong political power in physics affect how physics progressed and to adopt the gaseous sun? So for those who know physics, I think once you understand physics properly, you'll see that this is the only proofs required to say the sun must be condensed matter. You need a lattice. Now, if you look at the spectrum of the sun, it's indescript here. But if you blow it up, of course, there's a whole bunch of absorption lines. And these will tell us all the different elements that are present in the sun. Well, not all of them. The ones that that we're able to absorb light, and it's a really marvelous thing that we can see the elements in the sun. And this is the Fraunhofer spectrum of the sun over the visible range. Now, tomorrow, of course, there's going to be the eclipse. So this is what we'd all love to see. And hopefully I'll get to see it tomorrow as we're driving back home. Because unfortunately, we're leaving tonight. So for those who don't know that, if you want to talk to me after my talks, do come and see me. But if you look at the sun, of course, you have in the eclipse, you'll see the chromosphere and you'll see the corona of the sun. And the chromosphere is characterized, it has spicules. And way back in the 1800s, Angelo Secchi, who was a great astronomer, actually described the spicules of the sun. And he described it as small hairs on the surface of the sun. He was unbelievable as an astronomer. If you read his book, Le Soleil, which you can find online, you'll be amazed at the pictures of the drawings of Angelo Secchi in that text. And I've said that the spicules, of course, are condensed matter. Now, in the chromosphere, instead of the lines being in absorption, they're actually in emission. The lines are positive. In the previous depiction, the lines were inverted. And so the chromospheric spectrum is not quite like the Fraunhofer spectrum. It's not exactly a mirror. Many of the same elements, but some things are different. Now, the solar corona is what we'll be caring about. And this is for my son, Luke, who lives in Bradenton. And I just met, I think it was Gage. And he also lives in Bradenton.
It's Mike.
Mike lives in Bradenton, where one of my sons lives. Now, this is a beautiful picture of the corona because you see the moon in it. If you look at it, you'll see that the moon is in it. I love that picture. Now, what about the corona? Well, I think the main discoveries of the corona were actually done by William Harkeness. And I was lucky enough just a couple of weeks ago to contact the University of Rochester, which has the collection of Harkness's works. When he died, he was a University of Rochester graduate, and he sent all his papers there. And when I asked for things for this talk, they just sent me tons of files about Harkness's work. Now, that's nice for me because he's actually one of my favorite astronomers. So Patty was born in Iowa. And when I talked in my first paper about the corona of the sun, you'll see in the acknowledgement, I say, this is dedicated to my in-laws, which have given me the very best from Iowa. Now, I have to stop thinking about my wife if I'm going to get through this talk. All right. So this was Harkness's observatory in Des Moines. And Harkness made a great, beautiful work. Here's an eclipse picture from 1869. I think it's probably the first picture of an eclipse ever done. That was, you can find in the Harkness papers at the University of Rochester. So Harkness was an interesting character. He was born in Scotland, and then he died in New Jersey, but he became a rear admiral in the Navy. And during the eclipse of 1869, he noted that he had taken over 123 photographs of the eclipse, 2 being during totality. And he noted that he couldn't see any absorption lines in the corona, but it gave a continuous spectrum with one bright line in it, and that was a green line associated with iron-14. And so he was the first person to discover what is known as the emission corona. So he discovers the famous coronal line K1474, that's on the Kirchhoff scale. Today we know it's iron-14 at 5303.3 angstroms. But what he said about the corona is important to us today. because this is unlike what modern astronomy says today, but it's my position, is that the corona was a highly rarefied, self-luminous atmosphere which surrounds the sun and perhaps composed of an incandescent vapor of iron. So he thought that maybe his line was coming from iron, but the most important thing is that he was saying that the corona was self-luminous. So in the modern model of the sun and the standard model, remember that the light produced inside the sun is produced by an array of processes, none of which are thermal in nature, okay? So you have bound-free transitions, you have scattering, you have the negative hydrogen ion. All these things are contributing to producing this thermal spectrum. Now, the problem is in the corona, if you don't have condensed matter, well, now you can't produce the light in the corona. So in the standard model today, they say that the light of the corona is produced by scattering of photospheric light that's been scattered by relativistic electrons. So they have no means of producing the light because they don't want to put condensed matter inside the corona. But Harkeness had the answer, and the answer is that there is condensed matter in the corona. That's what you're seeing. The sun is sending out condensed matter into the corona, and it is self-luminous. Now, another evidence of this is that we do helioseismology in the corona. So I always try to remind the astronomers that seismology is a science of condensed matter. And so if you're doing seismology in the corona, you cannot do it in a vacuum. So if you look at the corona, there's several divisions of the corona. The K corona, which is the one that you will usually see in an eclipse, is polarized and it's devoid of Fraunhofer lines. In the standard solar model, it's photospheric light that's scattered by relativistic electrons. But in my model, it's just self-luminous condensed matter. The F corona possesses Fraunhofer lines. In the standard model, it's just photospheric light that's reflected by dust particles. But in my model, it's just that the corona is cooling and now becomes reflective. So you have condensed matter, it's farther away from the photosphere and it's cooling. And then the T corona is the thermal corona, and it emits its own light in the IR, and it's thought to be dust grains of 1 to 100 microns. Then there's also the sublimation corona, which is a region of emission of low ionized atoms produced by sublimation of dust particles in the cooler coronal areas. Now remember, they don't get to have cooler coronal areas. They're saying their corona is at millions of degrees, right? I'm saying that the corona is not at millions of degrees. You get emission lines in the corona because you have chemical processes going on there. So that's another major difference. So how do you get sublimation in cool regions if you're at millions of degrees? You don't have any cool regions. For me, I have cool regions. The E corona, of course, is the emission corona. In the standard solar model, it's caused by temperatures at millions of degrees. But in my model, it's chemical reactions that are involving electron capture. So what happens is that you have condensed matter in the corona, and this condensed matter is electropositive. So when you have a free iron atom, for instance, once it makes contact with that condensed matter, it'll be stripped of its electrons. It gets stripped of its electrons, and then it emits light devoid of electrons. It's only got 1 or 2 electrons left, for instance. You know, like you could even have iron 24, and then you'll get, as the electrons are transferred, when the atom breaks away, it then emits light. So I think that the idea that the corona is hot doesn't make any sense. The K, these are showing in this figure from NASA the position of the K corona, the E corona, and the F corona in terms of solar radii. Now, is the corona really at millions of degrees? Now, Allen, in 1946, he took the spectrum of the corona during the eclipse of October 1st, 1940, and he wrote, micrograms from solar distances varying from r equals 1.2 to r equals 2.2 6 of the solar radii show that coronal radiation reddens slightly as the distance of from the sun increases. So the corona is actually cooling. The micrograms, they become actually a little bit redder as you move away from the surface of the sun. So this is showing that clearly the corona is cooling. It's not hot. So I have a video, is the corona at millions of degrees? You can look at that on Skyscaler. And there's another fascinating one, the chromosphere cooler than you thought. And this is evidence from the carbon monoxide absorption line. Now, the reason that that's important is that the carbon monoxide absorption line is in thermal equilibrium. It's an absorption line. So it's reporting to you a real temperature. And what's happening is that the carbon monoxide line is decreasing in temperature as you move away from the solar surface. So that line is showing, oh, we are actually cooling as we move away. So in order to explain that, what the astronomers tried to tell us is that within the sun and the atmosphere of the suns, there's cooler regions and then there's very hot regions and so on, because they don't want to tell us that, oh, wait, it's actually not hot like we think it is. But in my model, this fits very nicely. We have 2 pieces of evidence that the corona and the atmosphere of the sun is cooling with elevation. So now when we talk about the sun, does it have a real surface or not? I mean, this is the whole issue, right? If you believe that the sun is a gas, so in the standard model, you have how they think that the sun is formed. They actually use the ideal gas law, and they invoke self-compression of the gas. They call it gravitational collapse, that slowly this gas will come and assemble. But you can't do that in an ideal gas, because in an ideal gas, the collisions are elastic. And because the collisions are elastic, there's no net collapse, okay? Any collisions that take place are perfectly undone. So when you try to make the stars gases, the thing that happens mathematically is you get something called negative heat capacity. So the stars are thought that as they lose heat, their temperature actually goes up. Okay, so this is a dilemma which is solved by Chandrasekhar when he introduces degeneracy in the white dwarf. But the problem is that gases don't have negative heat capacity. So the question is, well, how did a gaseous star gain negative heat capacity if the astronomers are right? So what I tell them is, look, guys, why don't you tell me how much mass do you need before a gas's heat capacity goes from positive, which all gases have positive heat capacity, to negative heat capacity? So I say that this is just, it doesn't work. Now, one of the problems with negative heat capacity, which you'll see in some of my last videos, is that you have the main sequence of the stars, and because stars have negative heat capacity, they have no means of cooling. So in order to cool a star, they have to take it off the main sequence, and they do all kinds of gymnastics. They make the star a red giant, and then it explodes and sends out, makes a nebula, and then comes down and collapses into a white dwarf eventually. They don't permit the stars just to cool down the main sequence. And this, I think, is just fantastic gymnastic, is what I call it in my video, that to require that the stars have to leave the main sequence in order to cool. Whereas for me, the stars just get to cool down the main sequence. So, so the stars are currently viewed as a gaseous plasma, which can be treated mathematically as a fully compressible ideal gas with negative heat capacity. This leads to the concept of black holes as massive stars collapse upon themselves. If the mathematics is reversed, this helps to account for how a point mass could result in Big Bang creationism. Now, in the standard model here, so what do you have? You have inside the sun, you have a core, and they say it's about at 16 million Kelvin. And then outside the core, Eddington invented a radiative zone where photons are just moving back and forth for millions of years or thousands of years before they escape as they slowly cool to escape in the photosphere. So you have this radiative zone, and then you have a convective zone, which we know exists. And then you have the photosphere. And you look at these temperatures, the convective zone is at 2 million degrees, but the photosphere is only at 6,000 Kelvin. Now, what do I say when I say 6,000 Kelvin? Now, Planck himself actually complained about this. If you read the theory of heat radiation, which is Planck's book, in there he complains about the astronomer setting the temperature of the photosphere of the sun. And he says that this temperature has something to do with the rays and it has nothing to do with the surface of the sun. Why does Planck say that? Because Planck realizes that for the temperature to be real in thermodynamics, that several things have to take place. And one of them is thermal equilibrium. You have to have thermal equilibrium. But if you have convection currents, which are known to exist on the sun, and you have conduction, then you can't have thermal equilibrium. And Planck must have realized that, and that's why he chastised the astronomers and told them that you cannot set the temperature of the sun this way. So what is this 5,800 degrees? For me, this 5,800 degrees has to do with the vibrational energy. So when we look at the sun, we have energy that's in translational degrees of freedom, and we have energy that's in rotation in vibrational degrees of freedom. And it's this component is what is involved in the vibration of the lattice. And that's why, so this gets back to, of course, graphite. Why is it that we get a thermal spectrum from graphite? Well, the only thing that you can invoke is the vibration of its lattice. And this is the same thing that I associate now with the sun. The vibration of a lattice is giving us this 5,800 degrees. Now, in the standard model, stellar stability is a balance of several forces. You have the gravitational force, and then you have gas pressure and radiative pressure that are moving against this gravitational force. So you're trying to keep all of these things in balance. And in the sun, gas pressure is thought to dominate, but in very heavy stars, then radiative pressure dominates. And I just have to shake my head, and people try to tell me that I don't understand gas pressure, and they need to go back and read the kinetic theory of gases. Gas pressure in the kinetic theory is produced at the wall of the container. And there is no wall in the gaseous sun. Now, interestingly, there's a very famous book by Clayton. This is not just an accident that I'm citing this book. This has been used to teach astronomy for years. And in this book, he has this sentence which I just love. The reflection or absorption of these particles from real or imagined surface in the gas results in the transfer of momentum to that surface. So here's a picture that's kind of similar to what's in his book. But how do you transfer momentum to an imaginary surface? It's just nonsense. There's no way that if you don't have a real surface, you can transfer momentum. And because in kinetic theory, the atoms that are within the container, at the center of the container, there's zero effect of all these interactions. It's only the interaction when the atom hits the wall there's a net transfer of momentum, and that results in the pressure, which is then transferred through the system. So I disagree with their claim that they can have gas pressure inside a gaseous sun because they don't have a surface. And people have made fun about this, try to ridicule me, but I still hold that when we teach about gas pressure in kinetic theory, we need to have a container. And the ideal gas law, by the way, I'm a chemist by training, the ideal gas law was done in containers, and that's how we are able to define a pressure. So in the standard model, the photons are produced deep inside the sun, and then they spend years bouncing around and eventually escaping. And this theory absolutely depends on the validity of Kirchhoff's law, and that's why I spent so many years showing that there is no valid theoretical or experimental proof of Kirchhoff's law. Now, how do we know that? So Kirchhoff says that the radiation inside a container will always be black and independent of the nature of the walls. And of course, there's two types of walls. You have the perfect absorber, like graphite, and you have a perfect reflector, let's say like silver, okay? But a perfect reflector, its emissivity is zero. and its absorptivity is 0. And in Kirchhoff's law, you get 0 over 0. And then Planck himself recognized that this is undefined. You can't have 0 over 0. So if Kirchhoff was right, that it was independent of the nature of the walls, the problem is one of his limits falls apart here. And so again, if physics believes that Kirchhoff's law is correct, let them show me a paper that shows that it's independent of the nature of the walls, and no such paper will be found. And I've searched for years. I can say that I probably know quite a bit about Kirchhoff's law of thermal emission. Now, Planck, in his text, actually tried to propose a proof of Kirchhoff's law of thermal emission, and that proof is easily dismantled, and I've published a paper showing the problems with Planck's proof of Kirchhoff's law. And I did that with Steve Crothers. So radiative transfer is present in the sun, but it becomes more important in larger stars. They have no meaningful conduction, which exists in ordinary matter, but this only becomes important in degenerate objects in the standard model, like the white dwarfs. And conduction cannot take place in the photosphere as its density is much too low. In the standard model, you're really in a vacuum at 10 to the minus 7 grams per centimeter cubed. So now the question is, does the sun have a real surface or not? I mean, this is such an obvious thing, right? So this is one of the simple proofs that the sun has a real surface. So if you look at the arrows that are flowing around the surface, we know that the sun has differential rotation, and there are currents going in the solid lines. But the solar wind is perpendicular to that. And so if this thing is a gaseous object, how do you get orthogonal behavior at the surface? That's impossible. So that's a very easy proof that most people can understand. This is another one that's quite nice. If you look at flares that have greater than 10 mega electron volts of energy, you only see such flares on the limb of the sun, on the edges of the sun, never in the center. And that's because what is happening is there's anisotropy there. The flare is not putting out photons in all directions. It's preferential in one direction. So when they're at the limb, we're seeing like a cone. It's emitting its light in a cone and nothing in the center like this. So this shows that at the surface here, there's anisotropy, and the flare is actually emitting anisotropic light, and that requires a real surface. Of course, I mean, when I look at solar telescopes, and Unzicker he did a video about this, like as telescopes get better and better, their arguments just are falling apart because now their resolution is becoming so great, and they're saying that their photosphere is 500 kilometers thick, but now they can see a pixel at 35 kilometers or so. So the resolution is just starting to be too great to say that this can be a gas now, because if it was a gas, you wouldn't get such detail. So as we push our telescopes more and more, we'll have no choice but to accept that this is indeed condensed matter. The other thing is that granules on the surface of the sun have a process called Baynard convection. Nowadays, they're trying to avoid the word Baynard convection. In the old days in astronomy, they said the granules possess Baynard convection. But today, you'll find that there's people writing papers that say, no, it cannot be Baynard convection. Okay, the problem is that Baynard convection is a surface-driven process. You have to have a real surface to have Baynard convection. And so Baynard convection, what happens is that the material flows up, and then once it hits the surface, then it goes down and then reaches the intergranular lanes, which are dark. Now, in the standard model, they say that the reason that the lanes are dark is because there's different temperature. Well, this is nonsense. I'm sorry, I shouldn't talk that way. I disagree with the way that they say it. See, Patty will teach me eventually. After 44 years, she's working on me. So I disagree with their explanation. And the reason is that we're essentially at one layer here. And what is happening is that you have, in physics, there's something called directional spectral emissivity. So in real materials, you don't have emissivity equal in all directions. Photons don't go equally in all directions unless you have a black body. If you have a non-black body, like a semi-metal, okay, you might get preferentially emission towards the normal and less emission on the side. So you get less emission, so it looks cooler. Now, this is the same thing that I'm saying in sunspots. In the standard model, they're saying sunspots are cooler. I'm saying no, they're more metallic, and metals have less normal emissivity than non-metals. So this is known. So we know that they're more metallic because we have high magnetic fields inside the sunspot. So they're more metallic, therefore their normal emissivity is going to be lower. This is known in condensed matter physics. So another one, does it have a real surface or not? If you look in the X-ray, this is a beautiful example, I think, that when you look at the sun in the X-ray, when you look at the limb of the sun, the intensity of the signal doubles. And that shows that you have a real surface. And then once you cross that surface in line 3 here, now you can see twice the length of, twice the amount of material. So there's a real surface there. This is Patty's favorite proof, and I really like this one. And Michael and Anastasia had actually interviewed the scientist that did this, Dr. Zarkova. I think she's a great scientist, but she tries to say these are like ripples on a pond when you have a flare that's breaking the solar surface, and you get these transverse waves on a pond, like transverse waves on a pond. Well, a gas can't do that. And what they tried to argue is that, okay, well, we have a gaseous sun, so now what happens is that we get a disturbance on the surface, it penetrates somewhat within the sun, and then it's magically reflected and comes and gives us the waves. Well, what's causing the reflection? You're just moving the surface from the surface to the interior. You haven't done anything. So transverse waves are a sign of condensed matter, and this, I think, is a clear proof that we have a liquid sun. Now, of course, a liquid sun is not my idea. And it's interesting, when you read the history of the sun, people had beautiful ideas, all kinds of nice ideas. One of my favorites, which I talked about in my history papers, which actually have been cited, my history papers have been cited by the astronomers. They even like my history papers. And they've been cited several times. And one of the ideas that I really liked was Herschel's. So when William Herschel was working in the 1800s, he really believed that the sun was inhabited and there were little Solarians that lived on the sun. But his problem was that it was so hot on the sun. So he invented his Solarians first. He wanted it to be inhabited. But then he discovers infrared radiation on the sun. And then he realizes that, oh my God, I'm going to cook my Solarians. What do I do? So then he invents a reflective layer to protect his Solarians from the heat. And anyhow, he ends up protecting them, and the Solarians live on in our thoughts. So there's beautiful ideas about the sun. And I think James Jeans was one of the giants of the sun. And he believed that the sun was a liquid, and that it was essentially, that the stars were liquid. Where his failure was he had built the stars from uranium and radium. And of course, when it was discovered that the sun was composed of hydrogen, he gave up his ideas. Now, James Jeans was a very interesting character. And he was, if you know the history of astronomy, you'll know that James Jeans was an advocate of liquid stars, and Eddington was an advocate of gaseous stars. Eddington was at Cambridge, and James Jeans, I think, was married to somebody that was wealthy, if I remember the story, and he did science, but I can't remember that he actually had an academic appointment, although he did his Adams essay, which is, if you know anything about Cambridge, you know the Adams essay is a great prize that people want to get in British science, and he won his Adams essay prize. He won the Adams Prize at Cambridge. So he was a brilliant guy. And he actually said that the stars were liquids. And he disagreed with Eddington, and they had back and forth arguments about is the sun gas or a liquid. Now, unfortunately for Jeans, I mean, he didn't have the right material. So if you read his books, his early books talk about a liquid sun and then liquid stars. He argues that the stars are liquid because there's a lot of binaries out there. And in order to explain the binaries, the easiest way to explain them is by a fission of a liquid mass. So you look at a star that's rotating rapidly, and there's old science actually by Darwin's nephew and others, Ritter, there's many, many others who studied rotating liquid spheres, and they can break and form binary stars. And this is one of his proofs that the sun should be a liquid. Now, he gave up the liquid stars, and he does it kind of quietly. He doesn't write anything. He doesn't say, okay, I give up on liquids, and he adopts gaseous stars. And when there's actually a book written about this on the history of astronomy that covers Jeans's works, and that when he writes the later version of his book, he clearly has adopted gaseous stars and resigned himself that his stars cannot exist. Now, so this happens in the early 30s. Now, if he had read some condensed matter physics papers at the time, in 1935, Wigner and Huntington proposed that metallic hydrogen could exist at high temperatures and pressures. And if he had seen that, he might never have given up liquid stars. So for me, some of you guys might know my story that I took out an ad in the New York Times. People thought I was a real nut when I did that. Anybody know about that? Who knows about it? Raise your hand so I can see who knows about this.
We've got a copy on our kitchen wall.
All right. So what happened, I had a friend who had trained with a Nobel Prize winner, and he worked in California. And I flew out from Ohio, and I went out to California, and we walked in Huntington Gardens, if anybody knows where that is, in Los Angeles. And I told him the sun is a liquid. And he's told me, he said, Pierre, you'll never say it. Nobody will ever let you say the sun is a liquid. And I said, well, what do I do? And he says, well, take out an ad in the New York Times. I said, now you got to be kidding me. You're not going to tell me to take out an ad in the New York Times. And he said, yes, Pierre. The thing that matters in science is that you say it and others know that you said it. That's all that matters. So if you write the equation, let's say you have a formula, you write it on the wall of the pharmacy building in spray paint, you give the drug and you say cures all cancers at this dose, and some idiot decides that he's going to synthesize your drug and try it and it cures all cancers, you did cure all cancers. So it doesn't matter where you say it. You must say it, and people must know you said it. So when we took out the ad in the New York Times, which was an enormous amount of money, it was $100,000 US at the time. And that was a lot of money for us. And Patty agreed that I could have $100,000 to be an idiot and say this in the Times. I shouldn't say idiot. Patty doesn't like that word. That I could do this. Could you imagine coming to your wife after you went to California and you say, oh, honey, can I have all the money we have? And I'm going to take out an ad in the New York Times to say that the sun is a liquid. So she agreed. I mean, I'm still amazed. So anyhow, I ended up taking the ad in the Times. And I had a very close friend at OSU, John Wilkins, which I talked about earlier. And John had come to OSU with Ken Wilson, who he mentioned. And they had come from Cornell together. And John was very close to me. I mean, he'd come over for Thanksgiving and Christmas. And he loved Patty. What's not to love? When he'd come over, John was terrible. He didn't want to talk to me. He just wanted to be in the kitchen with Patty. Get away, Pierre. And, but he spent many, many hours listening to me. And I knew that John did not start a workday without reading the New York Times. I mean, it was impossible. Okay. So what happened was I take out the ad in the New York Times on March 17th, and John's at the APS meeting in Indianapolis. The ad comes out, and it was like fury around the world. Everybody wanted to get a copy of the New York Times ad. And so the editor of PRL, Physical Review Letters, came up to John and goes, do you know this guy at OSU? Do you know this guy? And then he called his secretary. Did he send us a paper on the sun being a liquid? And he said, call his secretary to find out if he had rejected my work. This is the story I got from John. So the American Physical Society has a March meeting, and I decided to publish this article on Sunday, March 17th, which was St. Patrick's Day. I guess that's part of kicking the snakes out of Ireland. And I shouldn't say that. I don't want to say anything mean. But I did think of St. Patrick that day. And so the ad came out. And when I was on my computer, of course, the ad had a digital copy online. And it was unbelievable, the avalanche of people that came and looked at that ad. And of course, the New York Times distributes 2 million copies around the world, and this was printed in all the New York Times editions around the world. And when it happened, you know, I'd go to an APS meeting, American Physical Society. I was trying to tell people that you really should, if you have ideas, you know, people are sometimes hard on physicists, but it's the most democratic society you can imagine. If you're a member of the American Physical Society, they permit you to submit an abstract or a talk, a poster or a talk at any one of their meetings. And this is just something very laudable about the American Physical Society. So when I got into this mess, John told me, he said, Pierre, you got to join the American Physical Society. So I became a life member. So that was quite a few years back. So that day, I knew that John would read his New York Times, and sure enough, he was in Indianapolis, got his New York Times, and opened it, and then the collapse of the Big Bang and the gaseous sun, and then he told me, he said, boy, Pierre, I tell you, I kept my copy. Now, John is deceased today, and I was blessed to know him for about 20 years, and I would go into his office, and we'd speak about science. And I don't know, he never made too many public statements, I don't think. You never know how a physicist is reacting in private. For instance, when I said the sun was metallic hydrogen, I didn't know that John and Neil Ashcroft were very close friends. They were both at Cambridge together. Neil Ashcroft is one of the great condensed matter physicists, and he was the world's theoretical expert on metallic hydrogen. And so when I wrote the paper on metallic hydrogen, the 40 proofs, I sent the paper, and people think Pierre is crazy, I sent the paper to 60,000 physicists around the world. How that was done is through quite a collaboration of my family and my friends. And so you could go to every physics department, find the email addresses of everybody, and send them an email. I did it for 2 papers, WMAP or radiological analysis. I think that got 70,000 emails. And then the 40 proofs paper was mailed around the world. So nobody can say that they never got my 40 proofs paper because they all got it. Now, Raman, in his day, when Raman discovered the effect that won him the Nobel Prize, he had a secretary. And what he did was he told his secretary to send the paper to people, all the physicists, the prominent physicists around the world. So she started taking the paper and sending it all over the place. And she sent it to a group of Russians, I believe, who had discovered the same effect, but got to read Raman's paper that he had already published it. So he wins the Nobel Prize. So the thing is, in physics, even though people don't like my methods, it really doesn't matter how you communicate. You have to try to communicate, right? Don't give up. You got to try to communicate. So that's the lesson of this aside. Now, if you're a chemist like I am, you'll know that hydrogen is the little cousin of carbon. So there's a lot of beautiful interactions of carbon and hydrogen. And Wigner and Huntington, when they wrote their paper on metallic hydrogen, they actually specifically talk about graphite being a layered lattice, and this is one of the possible lattices of metallic hydrogen. Now, I talked a little bit about Neil Ashcroft and John. So Neil and John had gone to Cambridge together. Now, John had worked with Schrieffer, who was the Nobel Prize winner. He had become very close friends with Ken Wilson. But before he was at Cornell with Ken, he did his postdoc at Cambridge. So he did his PhD, I guess, with Schrieffer. I have his dissertation. John gave me his dissertation when he died, but I can't remember, but I think it was with Schrieffer that he got his PhD. And then he went to Cambridge to work and did his postdoc. And Neil Ashcroft did his PhD at Cambridge. So John and Neil were very close friends. And when John got hired at Cornell, he petitioned to bring Neil Ashcroft to Cornell. And I know this from his wife sending me correspondence. Now, this is after Dr. Ashcroft died. Now, it's when I sent Neil the 40 proof paper, of course, I didn't know he was John's friend because John never told me. He just got the paper and then wrote back to me. And in my response to a young man called Professor Dave online, I actually showed Neil Ashcroft's email. And Neil started corresponding with me, and one of the things he wanted to bring to my attention was this paragraph in a book article that I would have never seen had Neil not highlighted it to me. And so in this paragraph, he talks about, on little reflection, it is apparent that all the qualitative remarks just presented on the band overlap state in dense hydrogen could also have been made with minor modifications about graphite, a tetravalent hexagonal band overlap 1 atmosphere semi-metal. Accordingly, it is instructive to examine the known optical characteristics of graphite. In the visible range, graphite appears black. To some extent, these characteristics are reported to be shared by very dense hydrogen. One possible choice for the structure of dense hydrogen consistent with hexagonal symmetry is actually a graphite-like arrangement. So after I sent Neil the paper, then he sent me this, he said, Pierre, you have to know, I said this already, but I had already said in the 40 proofs paper, but Neil sent it to me. Then I found out that John and Neil were friends. And I said, well, John, when I said that the sun was metallic hydrogen, why didn't you tell me that you were friends with the world's expert on metallic hydrogen? And John says, Pierre, I'm here to listen. I'm here to listen to you. You have to work out the details, right? So John was a great person for that. He did not want to interject science, and that way you lose what was your contribution, right? If somebody starts giving you advice, then it's no longer yours anymore. But John was very prudent about that. He never interjected his own knowledge of condensed matter physics. Now, it's an interesting thing. In 1991, these guys, so metallic hydrogen, of course, the full metal is, it should be reflective, but I want, for the photosphere, more of a semi-metal like graphite. And these people claim that they had produced something that was very close to graphite. Now, I'm not going to talk about the microwave background here, but I did want to point one thing else about hexagonal planar lattices, because in water, when you shock compress water, it becomes optically black, completely black. So if you shock compress water, it'll go to thousands of degrees and become perfectly optically black. That's unbelievable. And when I first saw it, and this is an aside again, I'm sorry for my asides, but when I first saw it, there was an old professor, Dr. Bailey. He's probably dead now, but he was such a nice guy. And I was working on the AT, and Dr. Bailey was an expert in nuclear reactions and nuclear processes like nuclear reactors. He was an engineer, and he had worked in this area his whole life. So one day, he's helping me work on the patient table. He's an engineer, and he was helping me work on the patient table. And he comes into my office and he says, Pierre, I want you to read this book. And it was like on nuclear weapons. on the science of nuclear weapons. Now, of course, you're in medicine. You really don't want to read about nuclear weapons. But I love Bob so much that I decided I would read his book. And in that book, they talk about underwater nuclear explosions, and that when these explosions went off, the water became optically black for a moment. So the water becomes optically black, and then it becomes blue again as the shock wave goes through. So first optically black, then it cracks, the water becomes white. As it cracks, because you have a pressure wave that comes, and then you build a negative front, and once you close that negative front, it becomes optically white. So anyhow, these are things that Dr. Bailey and I've talked about in other talks, that Dr. Bailey brought this to my attention, that water can become optically black. And that's extremely important when you think about the structure of water. So I've said that the sun should have a hexagonal planar lattice. I first wrote it in this paper, which actually was cited in reviews of modern physics. It's interesting, I don't get cited a lot on the sun. Patrick cited me. He said he said in reviews of liquid plasmas that someday the liquid model, the gaseous model of the sun might soon be decrowned by the new liquid model. That's actually in the physics literature now. And I was cited in reviews of modern physics, but I think people are kind of scared to cite me. I get some occasional citations, but it's a big one to choose, so that's okay. So what I say is that the sun has a hexagonal planar lattice at the level of the photosphere. And what's interesting about graphite is that when you have a graphitic arrangement, there's strong interactions within the plane, but across the plane, it's actually a weak interaction. And you can have non-hydrogen elements enter those planes. And these are intercalate zones. And this is an extremely important idea to explain the formation of red giants and white dwarfs, not white dwarfs, supernova and red giants. And also the activity of the sun, that these intercalate zones get degassed when the sun gets active. And this is discussed in some of my papers, and we don't need to go too much into detail about that. But one of the important, you get blessed all kinds of ways in life. You learn music from your children because you're no longer listening to music, so they tell you this is what's going on in the world. And you also, I have three sons. One of them is in the Navy, and two others are physicians. And Christoph he was the professor's dream of a student, like this guy at OSU, there's like 1,500 kids that take Calc 1, and he was at the top of the class. When he took differential equations in his second year, he lost no points. I mean, nobody loses no points in differential equations. So he became a chemist, and he graduated summa cum laude with research distinction. Then he went to Chicago Medical School and so on. And I'm extremely proud of him. And he came up to me one day, and he goes, Dad, you're missing something. There's nothing like your son telling you you're missing something. And he was a chemist by training, and he said, if you adopt a graphite structure, then you're going to have intercalate zones. And this, I think, is actually the most beautiful idea about the liquid metallic hydrogen model of the sun, is the presence of intercalate regions. And they are so powerful to explain so many things. And I think that it's hard for me to believe that there is a better choice of a lattice than the hexagonal planar lattice for several reasons, which I made a video about it about maybe 8 videos back or so, of why this lattice has to be the right one. And one of the reasons is that the presence of intercalate zones and everything they offer to astronomy. And so that was not my idea. It was my son's idea. He said, Dad, you should If you got a graphite lattice, like, you're going to have intercalate zones. So I say that the photosphere is composed of metallic hydrogen, which is assumed to be graphite-like hexagonal lattice. Its internuclear distances within the lattice of such a material are such that it's a semi-metal. It's not highly conductive. But sunspots, facula, and the convection zones are comprised of metallic hydrogen, which has adopted a graphite-like layer, which is type 2. In this case, the internuclear distances are decreased and the material becomes highly conductive and able to support strong magnetic fields and the solar dynamo. So, you know, on the photosphere, it's more relaxed. And then as you go deeper, there's more pressure and that condenses it. And you could, I think Neil had some papers about when you condense metallic hydrogen, it becomes more conductive and more metallic. Now, the solar core, it should be metallic hydrogen. I believe a body-centered cubic makes sense. This was actually proposed by Setsuo Ishimaru. I learned about his work after I had proposed that the sun was metallic hydrogen, and in the 40 proofs paper, I actually cite him for the first time. He was an expert in high-density plasmas, and he wanted a metallic core for the sun, but he kept the core at an extreme density of 150 grams per centimeter cube, which is what is adopted in the standard model. That's where I disagree. I don't want a highly compressed core because we need material for the photosphere. So I think more like genes, that the sun has a relatively uniform density throughout. The corona possesses both free ions and atoms and a sparse distribution of metallic hydrogen, which is type 1, which has been ejected in the solar atmosphere from the solar body. The chromosphere possesses both free atoms and ions and sparse distribution of dense hydrogen, but not metallic hydrogen. So there could be some metallic hydrogen in there, but the coronal material should be more molecular in nature. And the transition zone does not exist, in my opinion. Now, there's something interesting. Remember when I talked about the inner granular lanes in the granules, that they're dark? If you look at the sun, it's brighter at the center and darker at the limb. This is the same thing. This is directional spectral emissivity. So in my model, this is explained with directional spectral emissivity. The normal is slightly brighter than the limb. And if you look in the standard model, the way that they explain the darkness at the limb, they say that the light is coming from the surface there, and in the center, it's coming deeper inside the sun, as you can see here. So in the center, it's coming from a deeper layer inside the sun that's hotter, and a cooler layer on the outside. But what I invoke is directional spectral emissivity, and that the emissivity of a non-conductor. So when you have a semi-metal, it's going to be more like A. It's going to have high emissivity at the normal and low emissivity at the ends. And then when you have a metal, a metal is kind of unusual. It has low emissivity at the normal, and then at some angle, it has high emissivity. Now that's interesting. Water is the same way. Water is like B here, okay? It's, now, let's go back. Water is acting, what I've tried to tell people is, water is like two things in one. We've got two emitters, and they're uncoupled from each other. And so what happens is that you have a 3 Kelvin signal from water, which is behaving like A. At B, you have a in water, if you look at the hydroxyl bond, when you're looking straight down on water, let's say at 1.4 gigahertz, you'll get like 100 Kelvin if you're looking straight down with the satellite. But as you look at the angle, at about 70 degrees, all of a sudden you're at 270 Kelvin. So you're at 100 Kelvin, and then if you move to about 70 degrees, now all of a sudden you get almost the right temperature for water, okay? So these satellites are always looking at an angle to get the the proper temperature, okay? But then if you move towards the limb of the Earth, then the temperature drops very rapidly towards zero. So water is, it's interesting, is water is behaving like B in the microwave, okay? But that's for the hydroxyl bond. For the other bond, the hydrogen bond, it's not behaving that way. So a black body has uniform emissivity. All right, so sunspots is a manifestation of lattice structure and directional spectral emissivity, not lowered temperature. I already mentioned that. So they're dark at the center because it's highly metallic there. And so because it's highly metallic, you have directional spectral emissivity that's causing, again, the emissivity drops. And then, since we're looking at the eclipse, I thought I'd just give a couple of slides about the chromosphere. The continuous spectrum of the chromosphere constitutes direct evidence that this region of the sun contains condensed matter. So we know that the chromosphere does have a continuous spectrum. And the chromosphere is the site of hydrogen recapture and condensation in the solar atmosphere, as evidenced by its emission spectra. So I'll give you an example of that. The chromosphere therefore acts to help conserve the mass of the sun by harvesting some of the hydrogen atoms and protons which have been released into the solar atmosphere. So the sun is releasing material, but it's also recapturing it, and it's condensing it in the chromosphere before it re-enters the sun. Now here's a very beautiful work by Erdel's group, and I don't know if Erdel's a Nobel Prize winner. He's a senior author on this paper, and it was just a magnificent paper. When I read it, I'm like, wow, this is just such a gorgeous paper. And the summary of it is you have a hydrogen cluster, you have a silver cluster with N silver atoms, let's say 4, and it interacts with another silver cluster. And when it does, it's going to form an activated complex of both clusters. Then it's going to emit a single silver atom, which is going to be activated. It's going to have an activated electron. So this guy here needs to relax. I'm pointing at a screen that you can't see. So in the middle there, where you have AgN plus M star, that's an activated cluster, okay? It needs to relax. What does it do? In order to relax, it kicks out a silver atom. So that silver atom is now activated, and now it emits a photon. So you've made now a large cluster. Now, that photon is going to be at high energies. Now, this was done at 10 Kelvin, so it's very interesting. I think it was 10 Kelvin. I'm an old man, so I might not know exactly the temperature, but I thought it was about 10 Kelvin. And so what happens is you get the cluster, it forms, but there's nowhere to dissipate the heat. Now, this is the same thing that's happening in the chromosphere, right? You don't have a place to dump the heat. Where are you going to dump it? So this is the lesson of this paper. When you don't have conduction available to you, what do? You emit a photon. So here, this is what I say is happening in the chromosphere. You have hydrogen clusters that are coming together, and then you can get hydrogen clusters. They're known to exist. And when they come together, you're going to get an activated hydrogen atom. And then it will relax and give you light. So this explains all the emission lines of hydrogen without making it a random process. So why is it that the chromosphere is emitting light? It's emitting light because it's doing chemical reactions. They're not random. And that's why the Fraunhofer spectrum is not the same as the chromospheric spectrum. This is involving chemical processes. The Fraunhofer spectrum is not. So here, let's have a look at condensation reactions in the chromosphere. HM here could be a very large hydrogen structure, right? Now you have magnesium hydride, and it's going to drop a hydrogen atom. So we know that magnesium hydride exists on the sun, and we drop the hydrogen atom onto a larger hydrogen structure. There's activation. Now we eject the magnesium atom, and now it relaxes and emits light. So these things can be used to explain why you have emission of light of all these atoms in the chromosphere of the sun. Whereas in the standard model, everything is random. Well, if it was random, and I have an example of this in one of my videos of helium lines, where you see the helium triplet lines and the helium singlet lines. And if you look at them in the laboratory, they have the same intensity, but in the sun, they do not. So they are not random. Something is selecting them, and the only thing that can do that is chemistry. So in the chromosphere, in the corona of the sun, the continuous spectrum of the corona exists, and it does not represent photospheric light scattered by relativistic electrons. It constitutes direct evidence that the chromosphere, the corona, is both self-luminous and relatively cool. It has, and as I showed you, it has an apparent temperature associated with its vibrational degrees of freedom, which is no greater than that of the photosphere and decreases with elevation. The highly ionized species in the corona, like iron-25, is associated not with temperature in the millions of degrees, but with the presence of condensed matter in the corona, which possesses an elevated electron affinity and thereby strips atoms of their ions and valence electrons. The corona is a site of electron recapture and works to help maintain solar body neutrality. It's a wonderful thing to see the activity of the sun, and this just shows how the sun, when it becomes active, emits a helium-2. It emits helium in helium-2. So this is now helium that's lost an electron, okay? Now, how do they explain that in the standard model? In the standard model, it's okay, what they say is, okay, now we have helium down here at the level of the chromosphere, and now why do we have it? How do we get helium-2? That takes very high temperatures. So how do they get it? What they say is that we have photons that are produced out here in the corona, and they come and ionize the helium. Okay, they ionize the helium, the electron leaves, and the other, so let's say you have the two electrons, and one of them leaves, the other one can then fall back down and emit light at 30.4 nanometers. So what I'm saying is, no, you don't need to have photons coming from the corona. If that was true, we'd be ionizing everything, right? Why do we have neutrals? We have neutrals because this is not happening. Coronal light is not ionizing helium, because if it had the energy to ionize helium, it would ionize everything else, but it doesn't. So that's not what's happening. So anyhow, as the sun goes active, you see an increase in helium-2 lines around the sun, and then that dies off when the sun goes quiet. So that's the end of part 1, and next time we're going to do eclipses, which will be more fun. Okay, God bless you, everyone.
Excellent. Greatly.
Thank you, thank you, thank you.
Okay, now the second talk is a little bit different because we're doing the eclipse, because I wanted to give a talk on the eclipses. Just this is the occasion for being here. I have my email on there if anybody decides that they want to contact me in the future. Now, it's an interesting thing about the moon. You know, the moon is, if you look at the distance of the Earth to the sun and the size of the moon to the size of the sun, it's a ratio of 400. And, you know, if you look at all the satellites of different planets in our solar system, there's 293 satellites. But only one, our moon, ends up giving us these beautiful eclipses. And this is a solar eclipse viewed from Mars, and you see Phobos in front of the sun there. And that's a NASA picture. Usually I remember to give credit, but anyhow, I said it orally. It's a famous picture. And this, I love, this was such a beautiful picture from Luc Viator. He just does such gorgeous photography. Now, so when you have a total solar eclipse, it always happens on a new moon. And it occurs about every year and a half on Earth. So the moon is interposed between the sun and the Earth. Now, if you look at this slide, it'll help you understand the process a little bit better. If you look at the ecliptic plane, that's the plane that the Earth is sitting in. Excuse me. That's the plane that the Earth is sitting in relative to the sun. That's the yellow circle there. And the moon is just out of the ecliptic by about 5 degrees. And when it is now in the, just 2 weeks ago, on the full moon, in descending mode, we had a lunar eclipse. And I told Michael and Anastasia, you know, there's going to be a lunar eclipse tonight. Because whenever you have a total solar eclipse, 2 weeks before you have a lunar eclipse. This is always true. So you're going to have a lunar eclipse beforehand. And this was on the descending mode. And on the descending mode, we had a full moon on the evening of March 24th and 25th. And then we're going to have our next descending mode eclipse will be an annular solar eclipse, which will be on October 2nd, 2024, and that will be a new moon. So there's a total solar eclipse, which is tomorrow, and it's a new moon again, and there'll be a partial lunar eclipse on the 17th and 18th of 24 on a full moon. So you can see here, these again are 2 weeks apart. So what happens is that the moon is crossing the ecliptic just at the right time, and then we get the beautiful solar eclipse. Now, the most important probably lunar eclipse, I love this story when I learned it. So Christopher Columbus knew he was in Jamaica, and the Jamaicans were starting to give him trouble. They didn't want to give him food anymore, and they didn't want to cooperate with him anymore. And he knew that there was a lunar eclipse coming. And he used it to have the natives in Jamaica listen to him and help him. And he had predicted the lunar eclipse and then predicted when it would go away if they listened to him. So they, of course, so this, I don't know if it was an abuse of science, but it's an interesting historical fact. There's a wonderful book, actually, Mary Todd. She's cited here at the bottom. Total Eclipses of the Sun. She wrote this book in 1894. It's a wonderful book. I'd love to get a copy of this book, but I think it's probably pretty rare to get an actual physical copy of your own. But in this book, there was a battle of the eclipse of Thales between the Medes and the Lydians, and during the battle, these guys had been fighting for like 5 years. It was a bloody war, and then during the battle, there was a total solar eclipse, and they made peace and intermarried, and that was the end of the war. So good things can come from solar eclipses. This was a shot of the eclipse that I went to see my son Luke, who's now in Bradenton with Mike, now that I know that Mike lives in Bradenton. And so I had gone out to Kansas City, and it was cloud cover, rain, thunderstorms. We went north. It was completely cloudy, and I said to Luke, I said, let's turn around. We're never going to be able to see the eclipse this way. So we turned around. We went east. We drove about a half an hour, and the sky cleared, and man, we saw the whole eclipse. It's unbelievable. So I wish you all the same tomorrow. All right. Now, just before totality, something interesting happens. If you look at a tree, you'll see that, so this again is in Mary Todd's book, and if you look at the tree here, under the tree in the shade, there's all these little crescents of the sun just before totality. And on buildings, you can see this undulating pattern, and most people are too busy looking at the sun, so they don't notice these things. And this is caused by turbulence in the air, the difference in density in the air that causes this turbulence. Now, so these are the prominent eclipses for us. There was the eclipse of 2017 is on this map. In 2045, I probably won't be around, but there is a parallel one on August 12th of 2025. And of course, there's the one today on the 8th. Our next closest one is in 44, but it only touches North Dakota, I believe that is, and Montana, and then goes into Canada. So, so it's kind of an unusual thing that we get to see an eclipse. The next total eclipse is going to be in Spain, I believe, in a few years. And then there's going to be 2 in Australia, almost back to back, I think in 28 and 30. And since my friend Steve lives in Australia, maybe I'll try to convince Patty that we could make one more trip to Australia. Now, eclipses are interesting in ancient civilizations. You know, people talk, when you read eclipse books, they talk about Stonehenge. I don't really know what the purpose was of Stonehenge, but Fred Hoyle, who is important because he believed in a steady state theory of the universe, he was, I think he's also the guy who coined the word Big Bang. He was making fun of the Big Bang. And there's a very famous paper on the nuclear reactions in stars, and Hoyle's one of the authors. And he argued that the stones and the holes in Stonehenge were used to predict eclipses. Now there's, of course, ancient civilizations have long been fascinated by eclipses. So in China, they thought that eclipses were caused by a dragon eating the sun, and people would make loud noises to scare the dragon away. And then eclipses were viewed as a bad sign, especially for the emperor, as they were no longer viewed as ruling with the blessing of heaven. So emperors therefore hired astronomers to predict eclipses so they could prepare for the event and warn the people. And I guess there was a dissatisfied emperor, Kang, who beheaded 2 of his astronomers for failing to predict eclipses in 2134 BC. But the math to predict eclipses didn't appear until the 1800s. So it's interesting, you know, when you talk about physicists, I mean, they don't have too bad of a lives, scientists. Nobody gets beheaded anymore. This was a beautiful, in the Metropolitan Museum of New York, there's this beautiful robe of an imperial robe, and you see the dragon eating the sun there at the center of the robe. The Mayan civilization, they associated eclipses with war and death. So for a lunar eclipse, they believed that it impacted pregnant women and children. They gazed at eclipses. No, they were pretty smart. They gazed at eclipses by looking at reflections on the water. Otherwise, they believed that the birds would come and take out their eyes. And they had religious ceremonies, sacrifices, and prayers to gods, which included the planets. And I believe that these Mayan women also tied a red ribbon around their baby. So they're pregnant, and they tied a red scarf around their baby to protect them against eclipses. Now, for me as a Catholic, Our Lady of Guadalupe is an icon of Mary, and she appeared in Mexico in 1531 to Juan Diego. And if you look at Mary in this icon, she's eclipsing the sun. And in the Bible, there's a few famous lines about this. The heavens declare the glory of God, and his firmament proclaims the work of his hands. And in Revelations, and I behold, when he had opened the 6th seal, and lo, there was a great earthquake, and the sun became black as sackcloth of hair, and the moon became as blood. Now, it's interesting. What was I going to tell you about this? During eclipses, it's a strange thing, but during eclipses, there tends to be earthquakes. And I could have spent more time pursuing this, but apparently it's a known fact that there are earthquakes near eclipse times. And I'm not an expert in this, but I just ran across it, and actually it was a good source, but I didn't pursue it. Now, Norman Lockyer is a very important scientist. He was the editor-in-chief of the scientific journal Nature. And we present him because he came to America in 1878 to look at the eclipse at that time. He's credited, along with Pierre Janssen, of discovery of the element helium. He led a total of 8 expeditions to see total eclipses of the sun. Now, Pierre-Jules César Janssen, this guy is an interesting character, okay? He was a co-discoverer of the element helium, and he was the first to recognize the gaseous nature of the chromosphere. So during the eclipse of August 18th, 1868, in India, he discovers the yellow line at 587.49 that will be eventually assigned to helium. And this is the interesting thing. During the siege of Paris, he used a balloon to see the eclipse of 1870, so he escaped Paris in a balloon to go see the eclipse. So, but now it turns out that it was cloudy and he never saw the eclipse. Janssen, in 1874, he took pictures of the transit of Venus. So I was very fortunate a few years ago to see the transit of Venus in Ohio, and I had a friend, but it was cloudy in Ohio, and I said, well, if we just go north on the weather report, it looks like maybe we'll see the sun. And so sure enough, we went north and saw the transit of Venus, which is just an unbelievable thing to see. The distance to the Earth is best measured through the transit of Venus, the distance to the sun. And we'll go through that a little bit. All right. So Janssen, he was just a great scientist. You know, he discovered helium. And so here's the transit of Venus. And the one I saw was on June 5th, 2012. And it was just a wonderful thing to see the transit of Venus. I was like so glad to be able to see it. And the next one will be in 2117, so we won't be around to see the next transit of Venus. And as you can see, they're like 8 years apart. So whenever you have one, 8 years later, you have another one. Now we're back to our guy, William Harkeness, and I told you guys, this guy was just a great scientist. And in 1874, he measured the astronomical unit for the first time. He measured the transit of Venus, and you have to measure the time of the first and last contact, and then using geometry and different points on Earth, you can calculate the distance to the sun. It's a tremendous calculation. The time will be different at different points on Earth. So the U.S. Naval Observatory, they sent 8 teams of observers to all these cities: Vladivostok, Russia; Nagasaki, Japan; China; the Indian Ocean; Hobart, Tasmania; Campbelltown, Tasmania; New Zealand; and the Chatham Islands near New Zealand. And then Harkness himself went to Tasmania, and he measured, after the trip was over, he measured the distance to the sun at 92,797,000 miles, and he was off by only 0.17% of the accepted value of today. He was an interesting character, and he wrote, he knew when the next transit would be, and he said the flowers will be blooming in 2004 when the next transit will occur. And that line is actually famous in astronomy. People know this line of, he had said that it'll be 2004 when the next transit would occur. And he said, what will the state of science, what will be the state of science when the next transit season arrives? God only knows. Not even our children's children will live to take part in the astronomy of that day. As for ourselves, we have to do with the present. And this is a picture of Steve Crothers. Yeah. Now, Steve lives in Campbelltown. Now, remember that Harkness went to Tasmania, and he went to 2 places. Now, I'm not sure that he went to Campbelltown personally, but his expedition went to 2 places, Hobart and Campbelltown. And when you go to Campbelltown, there's behind Steve, there's a building, and that's where the members of the Naval Observatory stayed. And this is a commemoration instrument of the transit of Venus in Campbelltown. And I was there just by chance this last October with Steve. It's a town of only 800 people, Campbelltown. It's not a big town. It's a village between Launceston and Hobart. And it's a lot of sheep and enormous farms. I mean, I went and saw a sheep farm there with a friend of Steve's, and this farm was 5 square miles in area. Now, Le Verrier was, now we'll switch from the transit of Venus to Le Verrier, because he was a genius in celestial mechanics. And Le Verrier, he looked at the irregular orbit of Uranus, and he predicted that a planet has to exist to account for this irregular orbit, which was the planet Neptune. And so he sent to Johann Galle a note saying, this is where this new planet will be, and go look at it on this date and look at this place in the sky, and you will find it. And on September 23rd, 1846, after only 1 hour of searching, Galle found Neptune only 1 degree away from what Le Verrier had calculated. I mean, and Arago, who was a very famous French scientist, I think a little overblown, I hate to say it, but because I know something about Arago. He was French. He wasn't doing just science. He was doing a lot of politics and so on. And he said that Monsieur Le Verrier vit le nouvel astre au bout de sa plume. It means he found a planet at the end of his pencil. So there's a picture of Neptune, the planet that he found from mathematics. Now, after discovering Neptune, Le Verrier considers the precession of the perihelion of Mercury, and this is extremely important in physics today. And he proposes the existence of an intra-mercurial planet called Vulcan in order to account for Mercury's behavior. So now I'm going to explain to you what Mercury is doing. So if you look at Mercury's orbit, it's oval, and it has a perihelion and an aphelion. And the perihelion is precessing this way. Okay, so you have a perihelion precession. And the question is, why does it do this? So people wanted to know. So Le Verrier, we'll go back to our guy here, he proposes that there's an inter-mercurial planet called Vulcan, and that's how you explain why Mercury is precessing this way. He wants to put a planet there, okay? So this becomes the obsession of this time in history. People start looking for the planet Vulcan, okay? So all the astronomers, they want to find a new planet. Now, there were people at the time, one of them you'll see in this talk, Watson, they were finding minor planets, you know, and they would spend all their time looking for minor planets. Now, Watson was so good at finding planets, he was in China one time and he found an asteroid, a minor planet, by just looking at the sky. He didn't even have a telescope, and he knew that there was a minor planet there. And he named it, and so he had discovered many large asteroids or minor planets. So this is important. Le Verrier is telling us, if there's a planet between Mercury and the Sun, this could account for the perihelion precession of Mercury. So everybody wanted to find this planet. So what happens here is now we go back in time, and there's an eclipse here, and you'll see that there's a line. So you see the one, there's a line, 1869, August 7th. That's the famous eclipse that Harkeness discovered, the coronal, the green line of the corona. Okay, and he said that the corona was self-luminous. See how it went right through Des Moines, Iowa, right through the center of Iowa. But then later, you'll see that on July 29th, 1878, there's an eclipse that's going through Colorado and Wyoming. So now this becomes insanity at that time to look for Vulcan. So here's a map, and Vulcan was thought to be a planet that could be about the size of Mercury and that could account for the perihelion precession of Mercury. So different teams went to different places. So you could see Pikes Peak is the lower circle and Denver is the upper. Now there's some famous characters that went to all these places. In Denver, there was Maria Mitchell. Now, if you want to know about a great woman in science, read about Maria Mitchell. So she was a great astronomer. She was a professor at Varsar College, which is a women's college. And she trained women to become astronomers. And a lot of them went on to Harvard to compute. Now, most people don't know this, but a lot of the computations that were done by these famous astronomers were actually done by women teams. These women were doing all the calculations. The men were taking all the credit, right? That's why they always say behind every great man, there's a great woman. But actually, it was the opposite, right? The women were doing all the work. Maria Mitchell wanted to go see this eclipse. And the government was paying people to go, but they wouldn't give her any money. And she went with her friends and managed to go and see the eclipse from Denver. She was a very interesting person. When she taught astronomy at the end of the year, inside the observatory, she would put out tables to graduate the girls that were seniors, and then she would write poems for every girl so that they would remember her. We don't have professors that way anymore. If you want to read about a wonderful woman in astronomy, Maria Mitchell would be one. There are others, of course, which I talk about in my papers. Charles Young was there. He was an extremely famous astronomer from Princeton, and he was also in Denver, also with Ranyard, who was a professor at Cambridge. So he had come all the way from England. At Pikes Peak, we had Cleveland Abbey. Now, that name doesn't mean much to you guys, but if you go back into the history of science in America, you'll know that Cleveland Abbey was quite an important character. And there was a General Meyer, and General Meyer was, I guess, like a general, he was a little bit too insistent on things, and it caused some discord. And then there was these people that ran a boarding house, a tourist, Sam Langley. Now, Samuel Langley, we have an Air Force base, I think it's called Langley's Air Force Base. And Langley is the one that first measured the thermal spectrum of the sun. Remember I showed you the very first slide, the thermal spectrum of the sun? Langley is the first one to have measured that, and his brother was there as well. So they were at Pikes Peak. And then in Wyoming, there's a town there called Rawlings, and next to it there's another town called Creston. And there's some big people that were at Rawlings. Thomas Edison went. And Thomas Edison had a device to measure the heat of the corona. But it was extremely, extremely sensitive, perhaps too much so. Okay, so he had a lot of trouble with his device. They had kind of built a cabin to protect his instrument. But if you just put your finger in front of it, that was too much heat. The needle would go off scale. Okay? And so he had figured out a way to measure heat from a distance. Henry Draper was an extremely famous scientist as well. I think he was a chemist. And, this I never translated it from French, but George Baker was also looking for Vulcan. Now, at Creston, we had our famous guy again, William Harkness. He was at Creston for this eclipse. So here is from the collection of I think from the University of Rochester, the eclipse at Creston, as this was as drawn. This is not a photograph. It was drawn. So at Separation, Wyoming, that's just right next to Rawlings. That's where Norman Lockyer was. I mean, the founder of nature. So Lockyer didn't want to come to the eclipse because his son was very ill. And he lived in England. And just before the eclipse, his son died. So then he came to see the eclipse. And then there's our famous guy, James Craig Watson. You don't know he's famous yet because I never talked to you about him yet. But the Watson Medal in astronomy is named after him. And we'll talk a little bit more about him as well. Lehman had come from Cambridge to go there. So think of these people back in 1878 going all the way down to these places. This was the eclipse as seen in Separation, Wyoming. And that comes from the Rare Books collection at the University of Rochester. Now, James Craig Watson, he was an unusual guy. He was one of the greatest astronomers of the 19th century. He discovered no less than 22 asteroids and minor planets. Okay? That's the guy that I was telling you. He was in China. He looked up at the sky, and he found an asteroid without a telescope. He knew the sky so well. He said, oh my gosh, there's an asteroid there. Okay? So he was a great scientist. He knew astronomy. But during the eclipse of 1878, he claims to have discovered not just one Vulcan, but two. Now, what happens is he claims to discover Vulcan, and he asks another scientist that's with him to please come and look in his telescope. And that person is too busy looking at his own telescope, so he won't come over and look at Watson's. So he gets an unconfirmed writing that he had discovered Vulcan. Now, what ends up happening is there's somebody else, I think he was from Chicago, who had reported Vulcan at the same position. He wasn't at the same meeting, but he had reported Vulcan at the same position. So Watson claimed that he had discovered Vulcan. Now the problem is that people started making fun of him. They started saying that, you know, he discovered not just one Vulcan, but two, and now pretty soon he'll have discovered four. So, you know, you can't rely on this guy, okay? Because, of course, the fame of discovering a minor planet would be tremendous, okay? So, he was not a nice guy. I hate to say this. So remember how you treat your wives, because years later, it could become known that you didn't treat her well. This is what, when he died, he bequeathed the majority of his estate to the National Academy of Science. And today we have the James Craig Watson Medal of Astronomy. It's one of the top awards that you can have today in astronomy. He left almost nothing to his wife, which he mistreated both verbally and physically, even in public. And I'm not just saying it, it's in books. So that's pretty bad when somebody's telling you that you mistreated your wife. And now, 100 years later, 150 years later, somebody is reminding people that you did. Now, why did I talk about this Vulcan stuff? I mean, why do I care about Vulcan so much? Okay, because about a month ago, I get an email. Now, it's amazing. You get emails, and I do read them. And this guy sends me an email, and he says to me, he says, you know, Dr. Robitaille, couldn't it be that we have the Minkov effect in the sun? Oh, gosh, I mean, I never thought about this. Well, it's, so the idea is that the sun has a core. We'll go through it. So basically, we're now presenting an abstract about the solid body rotation of the solar core in the liquid metallic hydrogen solar model. This is the title, Consequences for the Perihelion Precession of Mercury and the Possibility that the Zanikov Effect can account for the inversion of polarization associated with the solar cycle. So this is a pretty big title, but here is the abstract. Now it's going to be presented next Saturday. Now people wonder, I told you, you can go to the local APS meetings. For a while there, I was trying to go to all the local APS meetings, you know. So there's a Texas meeting. I once drove to North Carolina to see a professor and drove all the way to Texas to give a 10-minute talk at a Texas meeting of the American Physical Society and then back to Ohio. I can tell you that was a drive. And so there are local meetings of the American Physical Society, not just the big national meetings, and you can go and present a talk. And so what this abstract is about is about the solar core and its activity and how we account for it. So you know that the sun has activity. Here it is at 304 angstroms. And when the sun becomes active, of course, during the equator, we have sunspots. And there's a well-known butterfly pattern. These are different periods of activity. And the butterfly is made because, so at the beginning of a time, so let's say 1935, if you could find that, you'll see you're at the end of the tips of the butterfly, and most of the activity of the sun is going to be at relatively high latitudes. So when activity starts, it starts at high latitudes, and the reason you get the butterfly pattern is that as you approach the end of activity, the activity is more towards the equator. And then these are different solar cycles that you can see. So the question is, well, why do we get a solar cycle? Now, if you talk to the astronomers, they actually do not know. And they also have no explanation. And I think that we have a very beautiful explanation of the reason for the activity. So I go back to this paper with my son, and this is two things that I wrote with my son in this paper. The hexagonal metallic hydrogen layered lattice could provide a powerful driving force for excluding heavier elements from the solar body. Herein lies a new exfoliative force to drive both surface activity, flares, coronal mass ejections and prominences, and solar wind. Then later in the paper, that's from the abstract. Later in the paper, such lattice exclusion, now remember that we talked about lattice exclusion in this slide. We have intercalate atoms, and now we're going to expel them. When you get a sunspot, you're going to expel the atoms that are between the intercalate regions. So such lattice exclusion and the possibility that stars might undergo processes like exfoliation could play a crucial role in at least 5 separate aspects of solar and stellar dynamics. 1, supplying the driving forces for solar winds, the fast solar wind. 2, generating the setting for flares, coronal mass ejections, and prominences. 3, accounting for the 11-year solar cycle. 4, providing an alternative explanation for planet and satellite formation. So I've talked about this a little bit today to somebody in private, that the sun is, in the standard model, you know, you have a nebula and it collapses to form a sun, and then there's local fragments that form the planets. In this model, what I propose is that once the star starts forming its lattice, it excludes non-hydrogen elements, and it can do so violently, and this ends up forming some of the planets. Now, if you look at Jupiter, for instance, when a star is made, it can have high angular momentum, but the angular momentum of the sun in this model was transferred to Jupiter. Jupiter has an enormous angular momentum, so by excluding this material, now you've dealt with the angular momentum problem. So anyhow, whoops, was I done reading that? Oh, and explaining the existence of red giants and supernova. I just recently talked about this on Sky Scholar, so if you're interested, you can look at I think my last presentation on Sky Scholar. So what's the idea here that for our abstract? So the sun has a core, and this core is undergoing friction as it rotates. We actually know that there's shear forces in the region called the tachocline, which is between the core and what they now call the radiative zone, which I don't believe exists. I think it's the convection zone. So we know that we have shear forces there, and such shear forces can destabilize the rotation. So it makes the z-axis unstable. So as it rotates, it makes the z-axis unstable. Now, if you could just, this is similar to this effect, the Debenikov effect. This is what Floriano had proposed, but this is not actually, we don't have this actual effect. The Zanibikov effect is the intermediate axis is important. But in solid body rotation, if you destabilize one axis, you can get an inversion of it. Now that happens in a top. If you take a top and spin it, right, it'll have the spin axis, right, and it has other axes. If you touch the top, it will want to invert. So what happens is, so this is very different than the gaseous model. In the gaseous model, there is no solid body. They say that they have solid body rotation, but they're in a gas. You can't have solid body rotation in a gas. I'm in condensed matter, so I get to have solid body rotation. So as it rotates, it experiences friction. And when it experiences friction, the z-axis becomes unstable. So what happens is that it becomes unstable, and then it'll cause the z-axis to flip. And when it flips, what's happening? It's going to cause, as it gets ready to flip, the solar activity begins, and then at the maximum of solar activity, it inverts. So there are two unknowns in this problem. There's the rate of rotation of the core. Now, the astronomers tell us that the rate of rotation is 430 nanohertz. I don't believe it. Now, I cited it in my papers, but when you think about it, how did they ever measure a rotation that is so low? Right? Because they only have helioseismology to measure the rotation. Is that number really accurate? Now, there's probably 50 scientists that have said on that paper that we've measured the rotation of the core as solid body rotation at 430 nanohertz. Now, I will accept the solid body rotation part. Did they properly measure the rotation? How do you do that? Right? Because let's say this thing is almost spherical. How are you going to measure that rotation so accurately? So there's two unknowns in this problem. There's the rate of rotation of the core. How fast is it actually spinning? Is it really 430 or is it some other number? And the other thing that we need to know is, what's the asymmetry of the core? How asymmetric is it? Now, there's two knowns. There's the 11-year cycle. We know that. Okay? So we have two unknowns, and we have two knowns, the 11-year cycle and the perihelion precession of Mercury. So what I'm saying is now, so the perihelion precession of Mercury, you should know that this is one of the proofs of general relativity. So Einstein got this equation for the precession of Mercury, the perihelion precession of Mercury. But, whoops, this is not 1998, it's 1898. Okay, at the top I have it right. At the bottom I have it wrong. In 1898, well before Einstein, Gerber came up with the same expression. Okay? Einstein, when he came up with his expression, so this is the right expression for the perihelion precession of Mercury. When Einstein came up with his expression, it was highlighted to him that, wait a minute, Gerber came up with this expression many years before you did. And then Einstein got upset and he said, even if I would have known about his expression, I would have never cited it because I disagree with how it was derived and it's full of errors and blah, blah, blah. Okay? But that's not an excuse. Like, you have, somebody did something. You could say, I disagree with it. But you don't say, I would have never cited it even if I knew about it. That actually is dishonest. So I hate to say that Einstein was dishonest, but I consider, you can read about Gerber on the history of science, and what Einstein's quote is, it's about a paragraph of why he would have never cited him, and I disagree. In science, you cite, once you know that somebody did something, if you disagree with them, then criticize it, but don't say, if I would have known about it, I would have never cited him. So there's an equation now for the perihelion precession of Mercury. Now, remember, now we go back to our Verrier. What did he say? He said, well, wait a minute, I can explain the perihelion precession of Mercury by invoking Vulcan. Well, I don't want to invoke Vulcan, okay? I want to say that the core of the sun is slightly asymmetric, okay? That's the same as if Vulcan had existed. So if the core of the sun is slightly asymmetric, and if it has friction, when it rotates, it'll account for the inversion and the cycle of the sun every 11 years. Now remember, I also said we have to degas. So it's not just a simple problem of inverting the field. we also have to degas the sun, and we know that there's a moderate minimum. So at this period of time in the minimum, the sun didn't go active. Actually, in this period, in England, the Thames never thawed, like it had ice over the summer, okay, because during the minimum. So what I'm trying to say is that there are two things that are happening. You get the inversion of the polarization, and then that is associated with the degassing of the equatorial planes. You could read about this in my paper. But if the equatorial planes are already well degassed, there's nothing to degas, and that could explain the minimum. This will be presented next week. So I did use some text to help me in this presentation, and I just want to recognize them. This book by Barron, An American Eclipse, A Nation's Race to Catch the Shadow of the Moon and Win the Glory of the World, that was a great book. And that was a book that explained Edison and all these guys going out to Colorado and Wyoming to look for the eclipse. All right, well, God bless you all, and thanks for listening.
Thank you. All right, folks, let's take some questions.
Yeah, thank you so much. I'm sure there's plenty of questions on this one.
Dr. Robitaille, thank you so much for coming and giving the talk. I found it very engaging. Thank you. On the note of the liquid metallic hydrogen sun expelling non-hydrogen elements en masse in order to potentially produce large bodies, what's the minimum size of star that you think is capable of that? For example, would Jupiter be able to do it? If Jupiter's got similarly a liquid metallic hydrogen mantle or something like that, would it be able to expel a non-hydrogen body?
Okay, so Jupiter, I mean, people hypothesize that Jupiter, the interior of Jupiter is metallic hydrogen. And so maybe it has expelled some of its satellites. And I mean, somehow they have to get there. And now this is, you know, I'm not a planetary science guy, and nobody has ever considered these ideas before. And I'm getting a little bit old, so it's time for young people to say, okay, well, this part of Pierre's idea, maybe we could take it a little further or whatever. But I do think that the stars are expelling the planets. So next year, I finally got done the white dwarf this year, as I mentioned to somebody earlier in private. And I had been wanting to finish the white dwarf for a long time. The white dwarf, as you guys might know, the white dwarf is thought to be hyperdense in the standard model. And I'm saying, no, the white dwarf is not hyperdense. It is got a different lattice structure. The main sequence of the stars are metallic hydrogen and hexagonal planar structure for the photosphere. And the white dwarf has a lowered emissivity because it has a different structure. I propose that it could be something like diamond-like. So Eddington, when he made the white dwarf hyperdense, he just assumed that the emissivity of all stars was 1. He had made them gases, and he said they all have an emissivity of 1. But if you lower the emissivity, different materials have different emissivities. So if you lower the emissivity, then you wouldn't get an emissivity of 1, and now you wouldn't have to make these stars hyperdense. So the problem is the white dwarfs aren't very luminous. And so in order to explain that, Eddington said, well, we'll make the radius small. And that made the dwarf hyperdense, okay? And what I'm saying is, no, that was an error. You didn't have just radius to work with. You had emissivity to work with. And if you change the material that's causing the emission, then you can give it a regular density. Now, then what happened was astronomers said, no, we're going to prove to you that they're hyperdense. We're going to measure the red shifts on Sirius B. That's a well-known white dwarf, the closest one to us. And they measure the red shifts on Sirius B, and you'll see in my videos that I've analyzed the red shifts on Sirius B in great detail. And the problem is that all the hydrogen lines should give you the same red shifts, and the only red shift that they use is the red shift of hydrogen alpha. They should use all of them and tell us what all the red shifts are. But the other thing is that in the white dwarfs have metallic lines. And if the white dwarfs are super dense, then those metallic lines should have the same redshifts, right? But they don't. So what they do is they say, well, oh, the white dwarfs are all polluted. They get polluted by planets. So these lines don't belong to the white dwarf. Now they all come from pollution. So in order to fix their model, to keep the white dwarf hyperdense, they have to invoke now that we're polluting the white dwarfs with planets. And now, like beyond belief, they're trying to tell us that they're going to understand the planets around white dwarfs by looking at the metal composition of the metallic lines that came onto the dwarf. This is going to tell us how to analyze these planets that probably never even existed. So this is the whole white dwarf story is falling apart, I think. And if you look at the last 6 videos on Skyscaler, I think you'll come to understand why the white dwarf is in so much trouble. The redshift of the white dwarf hydrogen line, there's a kind of white dwarf called a WA white dwarf, like Sirius B is a WA white dwarf. And these white dwarfs have quasi-hydrogen molecules in their atmosphere. It is known. And such molecules can cause stark shifts of the lines. So instead of having a gravitational redshift like they think, it's a stark effect that's causing the shift. And this is, I've explained that in my videos. Now, I got distracted to the white dwarf. What was the question again?
So Luke's question was about whether or not the satellites of Jupiter could be caused by the bulk emission from intercalated layers.
I think I answered that. It's possible, but I'm not an expert. You know, I don't know. All right.
Amen.
Yes.
Dr. Robitaille, if you could be put into the position of having, say, NASA budget or what have you, what satellites would you put around the sun? How many? What would you be looking for? This is kind of a...
I don't know. I mean...
Or would you put a telescope up?
You know, there's so many problems on Earth, right?
Right.
So, you know, when we decide budget questions, you know, even though I like astronomy and stuff, I mean, I don't want to advocate for too many more satellites. People are starving on this planet. So for me, you know, look what's going on in Haiti. I mean, I don't want to talk about politics, but we spend a lot of money, and is that always well spent? I mean, we spend $1 billion on the Webb telescope. They think it's a great thing. I think, I don't know. I mean, we spend billions of dollars on nuclear submarines.
There are solar telescopes in orbit around the sun, around the Earth. Those are the ones I was thinking you might be interested in. I'm sure they're going to be putting up. I think India just put one up. There'll be other satellites put up.
I will look at the data, but if I had an unlimited budget, I don't know that I would invest it there. It's an interesting thing that discoveries, we have a lot of data already. I think what people need to do is carefully consider the data that we already have. They try to tell us we need more and more and more, and then, you know, now they wanted. I mean, they did the image of the black hole, right? When now they want to put satellites around the Earth so that they can get a bigger base for their interferometer, you know, so they can measure. You know, now we're going to get an image of a black hole. I mean, is it worthwhile for humanity? At some point, we have to start saying, let's look at the data. I mean, we have all this data on the sun, right? We can't even agree if it has a surface or not. Why are we spending more money? I'm sorry that I don't want to sound anti-science, but I think there's so many papers that people aren't even reading or thinking about. Why do I need more data? I can't even go through the papers that I have now. So this is why my wife is kind of frowning. She wants me to say, yeah, put more. You know, it's like when people want to go to Mars, right? Why? Why do you want to go to Mars? I remember when there was that Horizon well in the Caribbean, we couldn't plug that hole. So tons of fish died. And so maybe we should plug the hole in the Caribbean and then worry about what we're doing. I'm not, just because I work on the sun doesn't mean that I believe that we should be spending tons and tons of money on these projects. I think we have a lot of data, and at some point we have to say, what is humanity about, and do we need to spend more and more billions of dollars chasing these things. So I'm sorry to be kind of negative on that.
I mean, I think that that's a really vital way of looking at the scientific landscape, because I do think that there's this constant pressure of producing more and more, something new that you can put your name on and say that, you know, this is the results that I have collected and this is forever my data. And I think that if we slowed down a little bit more and thought more about the historical frame and thought more about what it was that we were doing, we probably would get better results.
Yeah, like one of the problems in science is that nobody reads history anymore. So we are working so hard to get our PhDs, and you know, when you start and your advisor is going to tell you something to do, and nobody reads the old papers. Therefore, they don't know what happened. So for me, when I started on the sun, I spent years just reading the history. I wanted to know what happened in the 1800s. And that's his point, right? History of science is important. And the problem with our PhDs today is they're coming out and they don't know the historical papers in their own field, the major landmark papers. They don't think about them because they're not taught critically to look at history. I think it's a real travesty in science today. So I would like to see young scientists look at problems and go back and see, can we reinterpret this data? I had talked to you about John Wilkins, and one time we were walking on campus, and I told John asked me, what can be saved in astronomy? And I said, I don't know if anything can be saved. We have data, but the problem is it has already been interpreted, and the young people won't have the courage to change the interpretation. So it is a big problem. Okay, next question.
Well, I've just uncovered my view of, or my fear of public speaking. Glad you could all be here for my question.
Take a breath.
So originally my question was about the, wow, I need to be really close to this thing. Originally my question was about the tachocline layer, but then you got into a discussion about it where I didn't expect it to be. and then you kind of answered my question, so I had different questions. And basically one of the things that you mentioned earlier was that I think you said that you thought that the sun should be relatively uniform in density throughout.
Yes.
So I guess what I'm trying to understand is how that jives with the existence of this portion of the sun that rotates like a solid body, and then this portion that I guess doesn't. Right.
So I'm invoking different lattice structure there. Ishimura had said that the core should be a solid body, body-centered cubic. And scientists do believe that the sun has a solid core. Now, I'm invoking a very different lattice for the photosphere and convection zone. So again, what is your question? And why is it uniform throughout? So if you go back in the history of astronomy, there were some very important papers in the 1800s looking at rotating liquid spheres. Now, this was done by astronomers and by mathematicians. And actually, Chandrasekhar, the Nobel Prize winner who worked on white dwarfs, he spent a large amount of his time looking at rotating liquid spheres that had uniform densities throughout. And that's because this is the alternative model, right? In the gas model, that's maybe called the Roche model, most of the mass is at the center of the sun, right? With a very high density, 150 grams per centimeter cubed. And then as you go out, the density drops, and then by the time you get to the photosphere, you're at 10 to the minus 7, right? But in a rotating liquid sphere, the density was always thought to be relatively uniform, and all that mathematics, all these papers exist. I mean, Schwarzschild wrote a paper about this. Chandrasekhar spent years of his life. He wrote a book on advancing our understanding of rotating liquid spheres. I don't think that Chandrasekhar cared about raindrops. He cared about the stars. Why would he spend 5 years of his life on it? It's because he knew that those old papers from the 1800s might come back and haunt everybody someday, right? And he wanted to put his mark on rotating liquid stars.
And
can I just clarify that? So, but you're saying that there is a portion of it that's the core is more dense.
It's essentially the same density. So the sun has a density of 1.4, and metallic hydrogen in metallic state, not semi-metallic state, should be about 0.7 to start. So if you want to put 0.7 on the exterior, you don't have too much more that you can go to put density in the core, right? Maybe you can make it 2.5, maybe 3, but basically you're making it uniform throughout, right? It's not a big like this is 100 times more dense, right?
Okay. And my other thing was just, so do you care to speculate on why the core might be asymmetrical?
I don't know. The thing is that it solves two problems with one stone. So in other words, when Einstein and Gerber solved the perihelion of Mercury problem, they were considering only one problem, right? But now we're solving two problems: the life cycle of the sun, or the inversion of the polarization of the sun every 11 years. Okay, so that is now tied to the perihelion of Mercury. So in this, we're using two things to solve one problem, right? So remember that we have to understand, why is there an 11-year cycle, which is not known. And now I'm saying that because of this effect of solid body rotation and making the z-axis unstable, now that causes the z-axis to flip every 11 years because the friction doesn't change. So we know that 11 years. Now we have to know, how asymmetric is this? And this gets back to the Vulcan argument and the perihelion of Mercury. So there is a slight asymmetry. It doesn't take much. So now that's something that actually there is only one solution. So even though I'm saying this can be solved, there's not a bunch of solutions. There's two problems: the rate of rotation and the asymmetry. And there's two parameters: the inversion time frame and the perihelion of Mercury. There's only one solution. How asymmetric is it?
Well, while we're on the subject, there's actually a question from the live stream about the irregularity of the perihelion. And the question is, why is it there? Is it because the barycenter of Mercury and Sun is moving as the core rotates, or is it because Mercury can't rotate fast enough to get ahead of
how you're solving it, right? With Einstein, he solved it with relativity, the perihelion of Mercury, right? Gerber solved it with a manner, and Steve Crothers is looking at this for us. And it seems like in Gerber's equation, in his equations, he cared about the x, y, z coordinates of the sun. That means he did not treat the sun as a homogeneous sphere. And that's what I need. Okay, but I'm not familiar enough with what Gerber did. There's a lot of mathematics in that paper. So Steve Crothers is doing that part. So let's be clear on to what happened here. Floriano's an interesting guy. He is a pilot, and he works for Verrier in England. And he trains pilots on 737s. So he's got a lot of experience training pilots. And that's where he learned about this effect, the Zabanikov effect, which, by the way, you should look online, because there's an astronaut that took a key in a shuttle. It might have been in a shuttle. And then he flicked the key, and the key came out of its socket, and then it spins, and then it rapidly inverts. And then rapidly inverts.
There's a really funny story about that, because the Russians actually discovered it, and they kept silent about it for 10 years because their scientists were convinced that it might happen to the Earth, and they didn't want to cause public alarm.
Yeah, okay.
And they later, I guess, calculated that the core was sufficiently stable that it was nothing to worry about.
I don't know. The poles of the Earth do shift. We know every 11.
They thought the whole thing would flip upside down, actually.
Really?
Yeah.
Okay, well, let's just let the core flip. Is that good?
Oh, yeah. The very last thing that I thought of was just when you were describing these, someone was, I guess, working on, spinning liquid spheres. Was that like an idea for like the creation of binary stars?
Yes, because when it spins, it can become pear-shaped and can cause a parent star and a smaller star. So Jeans argued that this liquid nature of stars was nicely used to explain the fission of stars to make binaries or tri-stars, 3 stars together. And so that was an advantage that's not shared in the gas model. Yes.
Oh, thank you for being nice, and Patty for helping with that. But you touched on this in a comment a few minutes ago, walking with your colleague who asked what from astronomy could be rescued. How about the distance ladder and Cepheid variable stars? Do you have a perspective on that, or supernovas, which are part of the cosmos?
Supernovas currently are made by accretion onto a white dwarf, right? So you have a white dwarf, it's hyperdense, there's a Chandrasekhar limit, and once you exceed that mass limit, the star explodes into a nova. So you have a white dwarf, and then it has an adjacent star, and it pulls the material from the adjacent star onto the white dwarf, and then it explodes. Now just think about what's happening here. Does this really make any sense that one star is going to give up its material magically to the other stars so they can explode? So what I'm saying is that the white dwarf has an ordinary density. Okay, supernovas happen because you have a star, an ordinary star, that has intercalate zones, and the intercalate zones become unstable, and then they explode, and that's why you get a supernova. Or if you get many layers of the intercalate zones, they can slowly increase, and now you get a red giant. So you don't need a white dwarf. So in my model, you don't need a white dwarf to make a supernova. A regular star can make a supernova. Whereas in the gas model, because they have to use changes in nuclear reactions and all this, you know, they're invoking all these strange things, right? And then, I call them strange, and then, I'm sorry, I shouldn't say that, probably Patty's going to frown on me. and then they invoke, you know, changes in nuclear reactions and so on. Why? Because they have nothing else. They have no lattice, they have no physical mechanism, so all they have is nuclear reactions. So they try to convince us that all the changes in the stars are happening because the sun is paralyzed, can't make any elements other than helium. Okay, and then all these other elements are made in other stars, and then they invent first generation stars to give us the elements. So our bodies come from first generation stars. The sun couldn't make us. It's just, so it's too much. You don't need a first generation star. Just let the sun make the elements. It doesn't make any sense. There's no reason to prevent the sun. And that's what I write in the paper, that they've crippled our sun in order to save their models.
Yeah, just to clarify for people who aren't aware of your white dwarf model, just quite simply, the white dwarfs are very bright, they're very dim, but they're very hot. And traditionally, the dimness is ascribed to them having a small radius. And what Pierre is saying is that they don't necessarily have a small radius. Their lattice is just different. So just like you can have a material like an atom like carbon arranged into a diamond, which is very optically transparent, you can also have carbon arranged into graphene, which is optically black. So by changing the lattice structure, you actually can get the appearance of a dimness. And it doesn't have to be a result of the size of the star shrinking.
Right. And the one thing about white dwarfs that I complain about is that I mentioned earlier, they're in WA white dwarfs, they're quasi-hydrogen molecules. That means it's not a hydrogen molecule. You got a hydrogen atom over here, and another hydrogen atom is approaching it, but it didn't make a molecule yet. Now, if this atom tries to emit light or absorb light when this one comes close to it, it's going to change the absorption coefficients and the emission coefficients. They're called the Einstein coefficients. Those coefficients will be changed because those coefficients demand the free atom. So when the people are working on white dwarfs, they don't talk about the quasi-hydrogen molecules that are known to exist in WA white dwarfs. And that is, for me, something that is really bad. They needed, every time they want to write about white dwarfs that are WA white dwarfs, they need to remind everybody that those stars have quasi-hydrogen molecules which can produce stark shifts, and those invalidate their red shifts and therefore their density measurements.
Thank you, Professor.
I'm not a professor anymore, okay?
Oh, okay.
Yeah, that's a title you have when you work for a university, but when you no longer work for a university, you're just Pierre.
Well,
right?
You taught me a bunch, so I still consider it. So, Professor Pierre, is there an affordable way to kind of test what's going on with the sun? I don't know, like, can we do like a multi-layer sensor probe that we can just fire into it and get some readings?
Actually, I had a friend, Dmitry, in Russia, and that's what he wanted to do, is send a probe to see the surface of the sun. But I think we have enough evidence. If people want to look, I mean, I wrote a paper, 40 lines of evidence for condensed matter. People need to look at these papers very carefully. Physics needs to go back and rule, is Pierre right or wrong on Kirchhoff's law? If I'm right on Kirchhoff's law, it all collapses. Now, this is what my belief is. I'm right because my friend John was the one person that I knew that was a condensed matter physicist, said, yes, you are going to prevail on Kirchhoff's law. Now, he's not around to say it anymore, so people can take that with a grain of salt. But I don't believe I missed Kirchhoff's law. It's a law that has no mathematical proof, and it's a law that has no physical experimental proof. Why is it a law of physics? That's a very important question. And if Kirchhoff's law collapses, then gaseous stars collapse and the CMB collapses. Because the CMB, the monopole of the CMB absolutely depends on thermal equilibrium at the time of recombination, okay, which is like 300,000 years or so after the Big Bang. So if you don't have Kirchhoff's law, that doesn't happen. That means the monopole did not come from there. So what I'm trying to tell people is the monopole had to be originating from a lattice, and the one that's going to end up doing it is going to be water. That's why I try to talk about water being optically black. That's very important, that water becomes optically black when it's shock compressed. And the reason is that when you shock compress a material, it doesn't have time to change its lattice. It's the shock is coming quickly. So the lattice already exists. You're just compressing it. So what is that telling us? The lattice is hexagonal planar in water because it's giving you optically hexagonal planar behavior. And also ice H1 with ice 1H, which is the most common structure of ice. It's thought that liquid water has a structure very close to ice 1H, which is, if you look at it, it's a puckered hexagonal ring. Okay?
Thank you.
So I know that you're so used to dealing with this, and we've talked about Kirchhoff's law several times, but we haven't actually said what Kirchhoff's law says. Now, yeah, go ahead. If you can summarize it, just so that people understand.
So Kirchhoff's law says that if you have a box, okay, and it's opaque, that means light can't go through it. It doesn't matter what you make the box out of. The radiation inside the box will always depend only on two things: the temperature of the box and the frequency that you're sampling. Only those two things. The walls do not matter. It doesn't matter what you make the walls out of.
So if it's made out of diamond or it's made out of carbon?
No, diamond is not opaque. It has to be opaque, right? The light must not go through the wall. Now the question is, there are two limits to this problem of opaque materials. One is the perfect absorber, and the other one is the perfect reflector. Those are the only two limits in opaque materials. Something is either absorbing the light perfectly or it's reflecting it perfectly. And we ignore transmission because if it has transmission, it's not opaque, right? So in light, there's three things that you could have. You can have transmission of light, it could be reflected, or it could be absorbed, okay? So we have two conditions. It's either absorbed or it's reflected. So in the perfect absorber, which is graphite, okay, Then you set up a black body. The radiation inside is as Planck would describe, except that graphite is not a good emitter in the low frequency range, okay? Long wavelengths like infrared and so on. So that's why they had to use platinum black. If you look at Planck's papers, when he got the equation, you look at the experimental papers that were involved. If Kirchhoff was right, they should have been able to make those black bodies from anything they wanted, because Kirchhoff said it's independent of the nature of the walls. But in actuality, when Rubens did the experiment, he used blackened metals. They used things to make that shape come out, right? Planck got the right shape, but they used specialized materials to do it. If Kirchhoff had been right, they wouldn't have needed to do that. And if you go to the NIST today, the National Institute of Standard and Technology, how do they make black bodies? They make them still from perfect absorbers like graphite. Okay, they don't make black bodies from silver cavities. Now, Planck, in his book, The Theory of Hate Radiation, I wrote a paper about this. In his book, Planck uses perfect reflectors everywhere. Okay, it's always perfect reflectors in Planck's book, except for one little thing. He always puts a little piece of graphite in the box. Why? Because that's a perfect absorber. Once you put it in the box, you've lined the whole box with it, right? It's a perfect absorber. So eventually, all photons that hit that piece of graphite will become thermalized and give you the black body spectrum. So Planck, he fudges, like he doesn't realize the importance of that he put the graphite piece in there. He said, okay, in a perfect reflector, any type of radiation can exist. But once I put the little graphite piece in it, it gets thermalized and it becomes black body. And he looked at that as the piece of graphite as a catalyst. It wasn't a catalyst. It was a perfect absorber. That's why he got the thermal spectrum. So this is a major problem in the history of physics. And it goes all the way back to 1859. Now, when Kirchhoff wrote his paper on black body radiation, it was theoretical. There was another guy called Stewart, and Stewart had written a paper a year before in 1858. And in that paper, Stewart actually does the experiment. Now, Kirchhoff did not do the experiment. His is theoretical. But Stewart actually does the experiment with plates. And then he ends up formulating Stewart's law that in thermal equilibrium, the emissivity equals the absorptivity, okay? How much it can absorb and how much it emits are related, right? So because it's in thermal equilibrium, you don't want to heat it up, right? So if it could absorb and get heated, you're not in thermal equilibrium. So it would absorb and then re-emit, so they're equal. That's Stewart's law. But if you talk to a lot of physicists, they think that the equality between emission and absorption, between emissivity and absorptivity, is Kirchhoff's law. No, it's not. It's Stewart's. Kirchhoff says that when you have a black body, the radiation inside that cavity is black and independent of the nature of the walls and determined only by temperature and frequency. That's Kirchhoff's law. So a lot of physicists can't even cite Kirchhoff's law correctly. They confuse Stewart's with Kirchhoff's. And by the way, that's the way it is on Wikipedia. All right.
Wayne, do you have a question?
Many of the studies I've seen about exoplanets around other stars seem to suggest that there's many things that they don't understand, such as hot Jupiters, which from the sounds of what you've just described in your answer to the previous question, it seems like the hot Jupiters are in fact, or could potentially be, these pear-shaped deformations that split off to create a nearby another planet or a star. Is that what you've described?
Okay, now next year I have my journey kind of planned for next year, God willing, and one of the things I want to talk about is this finding of exoplanets. Okay, so right now we have some exoplanets. There are several ways to determine that something is an exoplanet. One of the most convincing ways is a shift in frequency. If you actually see a shift in the frequency of the star, then you can tell that yeah, there's an object that's going around it that's causing this shift, okay? But a lot of times it's just the change in luminosity of the star. So the star is luminous and then it goes dim, and then it's luminous and then it goes dim, and then they have a period. But what I propose for that is you could be dealing with a change in lattice structure, that the star is at a junction between two lattice structures and it's just oscillating between the two. It gets heated a little bit, it goes into one, then it's a good emitter there, and then once it emits, then it cools down, it goes back to the other structure, and then it goes back and forth. So that could explain why you have these very, very short periods, you know? I mean, does it really make sense that we have a planet going around a star in just a few days? Like, some of them might be minutes, I have to look. But, so that's one thing that I want to address, is that stars are dynamic, and they could be changing their lattice structure dynamically, so that could explain the variables, and maybe a lot of these things that we're seeing in exoplanets that we didn't carefully consider the impact of lattice structure in stars. Does that help? And the pear-shaped thing could be part of it too.
Well, I think I got about 10 answers for one question. So thank you so much.
Hi, thanks for the presentation. And I got to say, I'm become a bit of a proponent of the liquid sun hypothesis, and I find it really interesting. But invariably, whenever I mention it to anybody, the first thing they tell me is, "But oh no, the sun, that's a plasma. Oh, it's not a gaseous model." And I almost feel like in the public perception, there is no gaseous sun. It's a plasma. It's a fourth state of matter. You know. Well,
the sun actually, to make them feel a little bit better, you should look at it as a one-component plasma. That's the answer. So the electrons are delocalized, they're flowing, and the protons are restricted to lattice points, and that's called a one-component plasma. You could actually look it up online. If you type one-component plasma, you'll see. And this is part of condensed matter physics, where they treat one-component plasmas. So the sun is still a plasma in the sense that the electrons are delocalized. Now, there's advantages to this, to have a one-component plasma. One of the things is that you get to have conductors and insulators inside the sun, if you will, that the electrons are going to be flowing in conduction bands, which are established by the lattice, the proton lattice, right? But in the intercalate zones, there's no ability to conduct electricity there. They should be insulators. So if you want to have set up a magnetic field by having a current going around, in order to control that current, you need a conductor, and you have to have an insulator as well. So in this model, you end up being able to put an insulator inside the sun and maybe explain someday, I won't be doing it, but explain someday the solar dynamo and all these things. Thanks. Okay?
Yeah. And then another quick thing, which was that I can't off the top of my head recall, but I follow Alexander Unzicker also, and in fact, it was one of his talks that first made me aware of this liquid sun hypothesis. And but in a recent video of his, he was like showing on the screen like, Robitaille would disagree with what I'm saying here.
And that's good. I like Alexander. So Alexander wrote a book on a liquid sun. And if you look at the book, in his book, he actually doesn't put a core in it. He actually makes it a plasma again in the interior. I told him, I said, you shouldn't do that, Alexander, because we know it has solid body rotation. So we can argue about what is the period of the rotation, but we know it's solid body. So by him making a gaseous plasma in the interior of the sun, I just...
Does he just want to preserve fusion in the gaseous fusion model? Is that his reasoning?
I don't know what his reason was, but I think that lattice confinement fusion makes more sense. That in my model, the protons are aligned, they're oscillating along the internuclear axis. And it's that oscillation and that probability of tunneling, you're bringing the two atoms, they're oscillating around a single axis, whereas in the gas model, they're not. So there's a big advantage for lattice confinement fusion in the liquid model. So why did Alexander do that? I don't know, but I still love him. I think he's a great guy. I didn't I really enjoyed going to Munich and meeting him. I met with him twice. The first time I went to Munich, I was going somewhere else and stopped in Munich. The second time I went to Munich was just exclusively to see him. And I realized that he's a person of some courage. And, he takes a lot of heat. But, I'm impressed with him. And when he wrote that in the book, I said, look, that's fine. I have a model, and that doesn't prevent other people from thinking. So let him think, let the facts will eventually determine if the core of the sun being solid makes sense, or do we want to leave it a gaseous plasma. Now, I did tell him that when the sun, in 1864, the sun was a bubble sun. It had a liquid exterior and a gaseous interior. So I told him, well, you actually went back to 1864. You know that, right? All right.
You might notice that most of the fusion projects, as far as energy is concerned, concern gaseous containment in magnetic fields. And I have a suspicion that that's a charming modality, since it's such a popular power generation model for harnessing fusion.
Right, but they don't have a net. They don't have
of course. I know it's not successful.
Yeah.
There are lattice confinement. There is one group, at least, that I found that did a lattice confinement through NASA, right. I think in Cleveland somewhere.
Right.
But they must be working on it in the basement or something.
Yeah, there is one paper on lattice confinement fusion. In 2013, I had written in the 40 proofs paper, at the end, you'll see that I talk about that this can enable fusion reactions, right? This idea that you're restricting the nucleus, right? So that's lattice confinement fusion. I didn't use the word lattice confinement. That's somebody else's word, but it's the same idea that once you have a lattice, you're going to be able to confine things.
So I feel like people are getting a little bit restless because we've all been sitting for a while. And I think that we should cut here. And then we still have a little bit of time before you leave. And so folks can ask you questions before time for that. And before you get out of that chair, I just want to say thank you, Pierre. You have guided us through so much. And
all right, thank you. God bless you all.